All right, here we are on question 3. I think I was talking a little low in the last video, but sound seemed okay if you turn it up. Yeah, I think I'm not going to redo it just because of time constraints, so I'm sorry if it's a little indistinct, but I think you should be able to see what's going on, even without my words if it really is low. But I don't think it is, as long as you have your speakers or headphones up. Okay, so question 3, 10 points in total. And we've got a generator, so that's our basic generator. We've seen that one a few different times, right about like that. Put it in the dotted box. And these are the output terminals that we're connecting to a transformer. And then to 3 light bulbs that, despite appearances, are all in parallel with one another, right? So, first, A, what type of electrical signal, AC or DC, must the generator produce for the light bulbs to receive current? Well, if you want to transfer any power from the primary, to the secondary of a transformer, you must have AC, right? A changing current in the primary creates a changing magnetic field, which is present in the secondary as well. If you have a changing magnetic field in the secondary, then you're going to induce voltage by Faraday's law. Now, of course, you don't have to put all that in this question, but that's the justification. So, type of electrical signal, better be AC. DC would just run current through the coil of the primary and make a very nice electromagnet, but nothing else. B, how does the generator produce electrical energy? By spinning a permanent magnet near some coils of wire. Explain in terms of Faraday's law. Okay, so I give you a big signpost. Basically, do you understand what Faraday's law is telling you? And we've been through this explanation a few times, so I'll make it a little bit brief here, and I'll try to sketch out a little explanation, okay? But here is Faraday's law, the form that we've been using. And remember that this right here, this part, is the rate change in magnetic flux, or as we've been saying it, number of magnetic field lines. And because when this magnet up here rotates, you have, of course, field lines coming out here, kind of like that, coming back around and going into the south pole of that permanent magnet, sort of like this. And so as this thing rotates back down here and this thing comes back up there, you are, at least for that part of the rotation, increasing the number of field lines present in this coil and in this coil as the south pole of the magnet comes up towards it. And then once it rotates past and back around, you're going to be then decreasing the number of field lines, and it comes all the way back around. You'll increase the number of field lines, but that is constantly changing. And so we know that we should induce a voltage from Faraday's law, okay? So induced voltage is there, and we have lots of this in our cartoon generator due to the rotation of the magnet. Okay, so I've given the verbally and written out sort of the version that you need there. That'll be worth a few points. It's one of the most fundamental things that we have for generators, and that's basically what I'm looking for. Okay, so moving on up here to part C. If the generator produces 24 volts RMS on its output terminals, what turns ratio is required for the transformer to produce 120 volts on its secondary? Okay. So it's a step-up transformer then, because we're going from a lower voltage to a higher voltage. And we know that the output voltage on the output terminals, that 24 volts that's mentioned, is the same as the voltage applied to the primary because there's nothing else in that circuit, right? So the primary voltage is 24, and the secondary voltage is 120. So that's 24 volts. This is 120 volts. And we know from our equation sheet that the turns ratio, NP over N sub P over N sub S, so the number of turns in the primary versus the number of turns in the secondary, is equal to this ratio in voltages. And so if we just sort of reduce that down a little bit, we find that the turns ratio is 1 to 5, okay, or 1 over 5, because 24 goes into 125 times. All right, so that's all we need to do. Nice and simple if you know what you're doing with your transformer stuff. And for D, what is the average power consumption of the circuit attached to the secondary winding? You may need to know that each bulb has a resistance. Oh my gosh, look at that. I thought I had eliminated all the typos. Well, one slipped through. Okay, in any case, I think that's pretty clear what I meant. Each has a resistance of 150 ohms. They are all three in parallel. So go back up to our little simple circuit over here. Right, we can draw from the top of that one to that side of that one and that side of that one, all through the same wire. And then over here on the other side, we can do the same thing. So the voltage difference across each one of those things must be the same. And so when we come back down here to the bottom part of the page, we can find the total resistance, because we need to, of that secondary circuit. So R sub T is just 1 over 150 plus 1 over 150 plus 1 over 150, all inverted, which gives you 50 ohms. Okay. Okay, so we'll need that. We know we do because we're looking for the total power consumption, the average total power consumption of that circuit. And so we need the total resistance, and we could go and find the current. It's actually going to come in handy down here. But the most direct way to do this particular part of the problem is to just recognize that average power, right, that's P with a bar over the top of it, that's average power, is equal to VRMS squared over the resistance, okay? So here we've got 120 volts squared, right? Because that's what shows up on the secondary winding of the transformer according to part C. And then we get our total resistance, and we divide one by the other, and we get something in the neighborhood of 280 watts. Let's double check that. You'll see me go, hear me go clickety clickety click here in the background. Do 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 do. Clickety click, divided by 50, 288. All right, there we are. Okay, now, lastly, assuming 100% efficiency in the transformer, how much RMS current must flow on the primary side to deliver the power you calculated in part D? Okay, there's a couple of different ways to do this, but if you just start at the beginning of the question and look at that, 100% efficiency means that there's no power lost going from primary to secondary. So P sub P is equal to P sub S. And if we write out what those mean in terms of current and voltage, then we have I sub P times V sub P is equal to I sub S times V sub S. And if we look at all of these things, we already know the primary and secondary voltages. And we only need to find the current, the total current going through the secondary side, and then we can use this to solve for I sub P. So let me just algebraically do that. Ta-da, okay, and we'll do our substitutions in a second. Okay, but we know from the previous part of the problem that R sub T on the secondary side is 50 ohms. So to get the secondary current, we just need to use Ohm's law. So 120 volts divided by 50 ohms is equal to 2.4 amps. Okay. And we can bring that right over there and substitute that in to get 2.4 times 120 divided by 24. And if you put all of that together, you get, clickety-clack, over here with my calculator, 288 divided by 24 is 12 amps. Okay, we can check my math on the other one. Great. And then, great, double checked. Good. So that's our current flowing through the primary. Notice that it's a step up transformer in terms of voltage, right? We're going from 24 volts to 120 volts. So up here, right, 24 volts to 120 volts. But that means the reverse must happen with current. So we're stepping down current. We're going from 12 amps to 2.4 amps. All right. So that's question 3. And the last video will go through all of the multiple choice questions rather quickly, just with brief, that's the word, explanations each.